Good morning. My name is Jonathan Dupuis, and I'll be going over the bomb calorimeter experiment. Alright, so the objective of this experiment is to measure the heat of combustion for an unknown fuel source using a bomb calorimeter. There we go. Then we compare that energy contents across various fuels. The principle is going to be based off the first law of thermodynamics. The calorimeter measures the heat released during combustion. Some key ideas is we're going to calibrate it with a known fuel source by finding the thermal capacitance of the system, and then we're going to use that to determine the heating value of the unknown fuel sample. Just touch on it. The thermal capacitance is the energy required to raise the temperature of the system by 1 degree Celsius. So here's the apparatus. The main components are the stainless steel bomb, which is pictured right here. It's got some lead wires leading into it with this little tray that will hold the fuel source. The wires that connect to the fuel source, and that's what causes the ignition. The thermocoupler, which you can see right here, number 6. And then it is in a container, a bucket full of water and a stirrer that will help move the water around, which is right here. And then it also has an oxygen. We also need an oxygen supply, which is going to be used to purge the bomb. Essentially, the fuel burns inside the sealed bomb, and the heat transfers to the surrounding water. And then the temperature rise is measured through the thermocoupler. So the procedures. You're going to prepare the ignition wire with the sample. You're going to make sure that the wires are touching the sample and it's not touching anything else. You're going to assemble and purge the bomb. You're going to do this 3 times. You do not want to exceed over 30 atmosphere. That's a safety concern. It could damage the bomb in other ways. You're also going to be purging the system to remove any impurities such as CO2 or nitrogen within the air. Then you're going to place in the water bucket 2 kilograms of water near room temperature. You're going to start data logging, then you're going to ignite the sample and then record that temperature rise. You're then going to repeat it for the unknown fuel source. So here are our results. Our unknown fuel source was a green Skittle, and on the right we have our known fuel source that we use to calibrate, which is benzoic acid. So when we compare these 2 graphs, you can see that on the bottom is our benzoic acid. This right here, we ran it for a shorter time. It is possible that caused an error and that I may have shut it off too early because it could have continued to rise, but you want to shut it off at equilibrium just so that way your data doesn't start going down. And in addition, you can see that since we did this first, we did not let the water cool down back to room temperature. On the second experiment with the green Skittle, it already started at a higher raised temperature. So for our calculations, to find the thermal capacitance, you're going to use the known heat of combustion of that sample, which is 1 kilogram, and then the observed change in temperature to get 14.7. Then we're going to use that to calculate the heating value of our Skittle, which came out to be 32.5 kilojoules per gram. When we compare that to the previous group's unknown fuel source, which was gum, you can see that the Skittle actually has a higher value than that, which, when you think about it, makes kind of sense. It has a lot more nutritional value than, not much, but a lot more sugar than a gum would have. Comparing it to other known fuels, we have wood, hard black coal, gasoline, natural gas, and of course, enritranium at the bottom with the most. So as you can see, you can use this to kind of judge where that energy release and stuff is compared to others. So some sources of error could be heat loss to the surroundings, incomplete combustion, temperature measurement lag, variation sample mass, or human error. Engineering applications to fuel categorization, energy efficiency and combustion analysis, and then used in power generation / material testings. So in conclusion, some key takeaways. You determine the calorimeter's thermal capacitance through a known fuel source, then we use that to find the heating value of an unknown fuel source. This helps demonstrate the first law in a practical form. Any questions?